Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Imagine looking up at the night sky, really looking, and asking that huge question, what's the ultimate fate of, everything?
It's the biggest question, really.
For decades, the answer seemed pretty set, if a bit chilling. The universe is expanding faster and faster.
Right, heading towards this sort of cold, dark, lonely end, driven by this mysterious anti-gravity stuff.
Dark energy, yeah. But what if? What if the very measurements that led us there had a kind of hidden flaw, a systematic bias?
Mm-hmm.
What if everything we thought we knew about the future of the cosmos is suddenly, maybe wrong?
That's exactly what we're digging into today.
We are diving into a challenge to a cosmological idea that's been around for, 30 years?
About that, yeah.
And it's a challenge so deep, it basically pulls the rug out from under the discovery that won the 2011 Nobel Prize in Physics.
It really does question that foundation.
There's this new, really meticulously researched study suggesting the universe isn't speeding up anymore. Might have actually switched gears and started slowing down right now, today.
Which is a huge turnaround.
So our mission today is to unpack these, frankly, remarkable findings. It all seems to hinge on correcting a subtle, maybe, but absolutely critical systematic bias in one of astronomy's most trusted tools.
The Type Ia supernova. The standard candle.
Exactly. And this isn't just, tweaking a number here or there. This could fundamentally rewrite the cosmic timeline and maybe change our whole understanding of the dominant force in the universe.
It's fascinating because of the sheer scale of what might need reorienting. We're talking about dark energy.
Yeah, the big mystery.
This unseen influence that makes up, roughly 70% of everything in the universe. Our standard picture, the Lambda cold dark matter model, or SCDM for short.
Right.
It's built on one massive assumption that dark energy is a cosmological constant. Its strength never changes. It's just there, uniformly dense through space and time.
Like a background hum.
Kind of. But now we've got evidence, pretty robust evidence actually, suggesting that this foundational pillar might be seriously flawed. Well, the analysis shows that what we interpreted purely as a cosmological effect, this accelerated expansion, might actually be tangled up with stellar astrophysics.
Yeah.
Specifically, how stars age.
So not just space stretching, but the stars themselves.
Exactly. It means our knowledge isn't just evolving, it's being fundamentally reoriented by looking really carefully at the data we already have. You really can't overstate the implications if you start questioning the gold standard of cosmic measurement like this.
Okay, let's definitely unpack that reigning cosmology first. Because to grasp how big this challenge is, we need to understand the foundation it's questioning. Yeah. Let's go back to the mid-90s and that incredible discovery announced in '98.
Right. Before then, the expectation was pretty straightforward. You have the Big Bang, this initial huge expansion.
17.8 billion years ago, roughly.
Right. And then gravity, the pull of all the matter, should have been putting the brakes on, slowing the expansion down.
And for billions of years, that seemed to be the case.
It was. Gravity was in charge. The universe was sort of coasting, decelerating gradually.
But then something changed.
Exactly. Two independent teams of astronomers, the Supernova Cosmology Project and the HISE Supernova Search Team, they were using distance measurements, looking way back in time, billions of light years away.
Seeing the universe as it was long ago.
Precisely. And their results were shocking. Around 9 billion years after the Big Bang, something flipped. The slowdown stopped, and the expansion actually started to speed up again.
Whoa, okay.
Yeah, whoa is about right. That accelerating push needed an explanation. To overcome gravity's constant pull, you needed something pushing back, a repulsive force, some kind of inherent energy of space itself.
And that's what got called dark energy.
That's it. It acts like this anti-gravity, pushing distant galaxies away faster and faster. And this discovery, based on using these distant supernovae as cosmic mile markers, was so revolutionary. Well, it deservedly won the 2011 Nobel Prize.
And really cemented the idea that the universe was accelerating and would just keep doing so. Forever, maybe.
That became the standard picture.
And the key measuring tool for all of this was the Type Ia supernova. Why were they considered so reliable? Why the standard candle?
Well, they were thought to be anyway. The core idea is pretty neat. Type Ia supernovae happen in binary star systems. You have a white dwarf, which is a dense remnant of a star like our sun, and it's pulling material off its companion star. It accretes mass bit by bit until it hits a very specific limit, the Chandrasekhar limit, it's called, about 1.4 times the mass of our sun. When the white dwarf reaches that exact mass, it becomes unstable and just, boom, catastrophically detonates.
Okay, so the trigger is always the same mass.
That was the crucial assumption, because the explosion mechanism was thought to be identical every time hitting that specific critical mass. Astronomers assumed these explosions would have a highly uniform intrinsic brightness. Their absolute magnitude would always be the same.
Right, like knowing you have a perfect 100-watt light bulb.
Exactly. If you know its true wattage, its intrinsic brightness, you can figure out how far away it is just by seeing how dim it looks from Earth.
The dimmer it appears, the farther away it must be. Simple physics.
That was the principle. So when astronomers looked at these really distant Type Ia supernovae, the ones with high redshift that exploded billions of years ago, they found they were significantly dimmer than you'd expect if the universe was just decelerating or even coasting.
Dimmer than they should have been.
Right. And the interpretation of that unexpected dimness was purely cosmological. Meaning the thinking went like this. They look dimmer, mostly because space itself is expanding faster, carrying these distant galaxies away from us more quickly.
So the light gets stretched out more, diluted by the accelerating expansion between us and them.
Precisely. More distance, more acceleration, meant more dimness. And that required some kind of constant, pervasive, repulsive force pushing everything apart.
Dark energy, the cosmological constant.
Exactly. And that's how we landed on the consensus view, the MLCDM model. The universe is still accelerating today, and dark energy is constant. Its strength doesn't change.
If we get technical for a second.
In technical terms, the equation of state parameter for dark energy, often written as W, is assumed to be exactly -1.
W equals -1.
Right. And W equals 1 means the dark energy density is constant. It behaves exactly like Einstein's cosmological constant, lambda. And that constancy, that W equals 1, is the core pillar that's now being seriously challenged.
Okay, that brings us right to the new evidence. And this is where the science seems to be finding cracks in that seemingly perfect standard candle. This work comes from Professor Youngwook Lee and his team at Yonsei University, published recently.
Yes, in monthly notices of the Royal Astronomical Society.
And their core idea is, well, it sounds simple, but the implications are huge. Type Ia supernovae are not perfect standard candles. Their brightness is strongly, systematically affected by the age, and crucially, the chemical makeup, the metallicity of the stars that blew up. And that has nothing to do with how far away they are.
This is the subtle point that potentially changes the whole cosmic calculation. See, astronomers already knew supernovae weren't perfectly identical. They applied corrections, luminosity standardizations, based on how quickly the light curve faded the stretch and its color.
Right, trying to iron out the small differences.
Exactly. But the Yonsei team showed that even after you apply those standard corrections, something else still matters a lot. The underlying stellar population. The age and the metallicity, the amount of heavy elements in the stars that eventually became that white dwarf.
Okay, so explain the systematic bias. How does age or metallicity mess with the brightness?
Well, let's break it down. Think about the early universe. Stars formed back then, and stars in younger star-forming regions today tend to be metal poor. They have fewer elements heavier than hydrogen and helium.
Okay.
The finding is this. When a Type Ia supernova comes from one of these younger, metal-poor stellar populations, that supernova appears systematically fainter, intrinsically dimmer than its cousins from older populations.
And conversely?
Conversely, supernovae that come from older, more metal-rich populations like you'd find in more evolved galaxies appear systematically brighter.
Hang on, why? Why would the amount of metal or the age of the system change the brightness of an explosion that's supposed to be triggered at exactly the same mass, that 1.4 solar mass limit?
That's the key stellar astrophysics question they seem to have answered. The leading theory relates to how metallicity affects the progenitor system. In environments with fewer heavy elements, the winds from the companion star might be different. Maybe the structure of the white dwarf itself just before it explodes is subtly altered.
How does that change the boom?
It seems to affect the thermonuclear runaway, the explosion physics itself. Basically, a lower metallicity environment seems to lead to a lower yield of radioactive nickel-56 during the explosion.
Nickel-56, that's important.
Critically important. Nickel-56 decays into cobalt-56,
Yeah.
and that radioactive decay chain is what primarily powers the peak brightness of the supernova's visible light. So less nickel means less fuel for the light show.
Meaning less intrinsic brightness.
Exactly. A metal-poor, younger system produces a less bright explosion, even if it started from the same mass trigger.
Wow. Okay, so the implication for cosmology is, if you're looking way back in time at the most distant supernovae.
The ones used to prove acceleration.
Right. You are inherently looking at younger stellar populations from a time when the universe was less chemically enriched.
Correct. Less metal-rich overall.
So those distant supernovae were already intrinsically functor to begin with, just because of when and where they were born.
That's the core argument. They look dimmer for two reasons. Yes, they're far away and subject to cosmological redshift and expansion effects, but also they were just less bright from the get-go due to this stellar age metallicity bias.
Which means the amount of dimness we blamed entirely on acceleration.
Might be significantly overestimated. Part of that dimness is just astrophysics, not cosmology. It weakens the case that acceleration alone caused all the dimming we observed.
That makes a lot of sense. But hang on, if this effect is real, how did the original Nobel-winning studies miss it? Was their data not good enough, or?
That's a fair question. It wasn't necessarily a flaw in their methods at the time, but more a limitation of the data samples they had and the instruments available back then.
Okay.
To really nail down this bias, you need to accurately measure the age and metallicity of the host galaxies for hundreds of supernovae, covering a huge range of cosmic time or redshift.
You need to know the neighborhood the star lived in.
Precisely. The Yonsei team used a much larger, more modern sample, 300 host galaxies. And crucially, they used detailed spectroscopy and color magnitude diagrams. They looked at the precise colors and spectral fingerprints of the other stars in the host galaxy to really pin down the age of the stellar population that likely spawned the supernova.
So they did detailed demographic studies of 300 different galactic homes for these explosions.
That's a good way to put it. And this much larger, more detailed analysis gave them the statistical muscle they needed to isolate this subtle effect, this systematic trend.
And the confidence level.
That's the kicker. They confirmed this age bias exists at an extremely high significance level, 99.999% confidence.
Wow, 99.999%. That's basically certain.
In statistical terms, yeah. It means the chance of this correlation being just a random fluke in the data is incredibly tiny, vanishingly small. It strongly suggests this bias is real and must be accounted for when using supernovae to measure cosmic distances.
Okay, here's where it gets really interesting then. This finding means that the dimming of those distant supernovae, which we previously chalked up entirely to faster and faster cosmic expansion, actually arises, in a significant way, from stellar astrophysics. From a flaw in our standard candle itself.
And that connects the dots directly back to the acceleration problem. If those distant supernovae look dimmer, partly because they're intrinsically fainter due to their age and metallicity, not just because space stretched faster,
then our calculation of how much faster space was stretching must be wrong. It must be inflated.
Exactly. We attributed all the extra dimness to acceleration, but if a chunk of that dimness was just the star being young and metal poor, then the actual cosmological acceleration effect must have been smaller than we calculated.
Okay, so when you apply this correction, this 99.999% certain correction, you have to go back to the drawing board with the data, right? See what the universe actually looks like according to these refined measurements.
Absolutely. You have to revisit the historical data and see what the new numbers tell you.
And what do they tell them? Did the corrected data still fit the standard model?
No, that's the crucial point. The researchers took the raw supernova data, specifically using large data sets like the Dark Energy Survey. They applied their systematic age bias correction, and then they tested it against the standard CDM model.
The one with constant dark energy, W equals 1.
Right. And unsurprisingly, the corrected supernova data no longer matched that model. There is a clear discrepancy.
How did they show that? Visually?
Yeah, they use something called the Hubble residual diagram. It's a really important tool. It basically plots how much the observed brightness of the supernovae deviates from what a specific cosmological model predicts at different distances or redshifts. If the universe behaved exactly like the standard constant dark energy model says, then the data points on this plot, after the standard corrections, should basically fall along a flat horizontal line, meaning no systematic deviation.
And did they? Before this new correction?
Loosely, yes. The uncorrected data after standard stretch and color fixes kind of scattered around that flat line, which supported the ACDM model, more or less.
But after the Yonsei age bias correction.
Big difference. The corrected data points showed a clear, significant systematic shift away from that flat line. Instead of staying flat, the corrected data traces a curve that deviates significantly from the constant dark energy prediction.
A curve, meaning the deviation isn't random, it changes with distance or time.
Exactly. And that deviation immediately tells you that the cosmological constant model, lambda, is probably wrong. It doesn't fit the refined data.
So if the standard model is out, what does fit the corrected data better?
The corrected data aligns much, much better with models where dark energy is not constant. Instead, the data supports models where the density, and therefore the repulsive force, of dark energy actually weakens and evolves significantly over cosmic time.
So WUM isn't stuck at -1.
Exactly. It suggests W is dynamic. Maybe it was more negative in the past, driving acceleration, but perhaps today it's slightly greater than -1, indicating a force that's decaying, losing its punch.
You know, this sounds familiar. Haven't there been other hints recently that dark energy might not be constant?
You're absolutely right. This fits with growing evidence from other corners of cosmology.
Like the DSSI project.
Exactly. Just last year, results from the Dark Energy Spectroscopic Instrument DSI, based in Arizona, which looks at how galaxies cluster together, already hinted that the strength of dark energy might have changed over time.
So DSI was seeing potential evolution in W2.
Yes, their data, derived from these large-scale structure patterns, pointed towards a dynamic W. So the idea of evolving dark energy wasn't completely out of the blue. But this corrected supernova data provides really strong, independent confirmation. It brings the supernova measurements into alignment with those other hints.
Okay, so bringing it all together, the corrected supernovae may be combined with other data. What's the bottom line on the standard CDM model?
The bottom line, according to this analysis, is that the combined data rules out the standard CDM model with overwhelming significance.
Overwhelming significance, not just a maybe.
No, this isn't a small statistical wobble they're reporting. It's presented as a definitive rejection of the current consensus model based on this corrected evidence.
And if you reject the constant dark energy model, you have to accept the alternative scenario that does fit the corrected data. What does that imply for the expansion of the universe right now, today?
It implies something truly profound. It means the universe is not accelerating today, as we've thought for the last 25 years.
Wait, say that again?
The analysis suggests that the universe has already passed peak acceleration. It has transitioned into a state of decelerated expansion. It's still expanding, but the rate of expansion is now decreasing.
So, we are currently living in a slowing universe.
According to these findings, yes, Professor Lee stated it very clearly. He said, the universe has already entered a phase of decelerated expansion at the present epoch. And that dark energy evolves much faster than previously thought.
That is a complete reversal of the picture that won the Nobel Prize.
It's a massive shift in perspective. The expansion is ongoing, but gravity seems to be slowly winning the tug of war again, causing the rate of expansion to slow down.
It's incredible to think about these cosmic transition points. You had the first 9 billion years or so, gravity slowing things down.
Acceleration, right.
Then dark energy kicks in, becomes dominant, and speeds things up for a few billion years.
Acceleration, the era we thought we were still in.
And now, if this is right, because dark energy appears to be weakening, gravity is starting to reassert its influence on the largest scales, causing the expansion rate to slow down again.
The dominance of forces seems to have flipped once more. It's a much more dynamic cosmic history than the standard model suggested.
What really gives this study punch, though, isn't just the statistics on the age bias, right? It's how it clicks with other measurements.
Absolutely. That's perhaps the most compelling part. It's not just the 99.999% confidence in the correction itself, but the fact that when you apply this correction, the supernova data suddenly aligns beautifully with independent ways of measuring the universe.
Methods that previously didn't quite line up with the supernova result.
Exactly. Measurements that had been kind of quietly problematic because they just didn't agree with the gold standard results from the potentially flawed supernova method.
Okay, let's talk about those independent data sets.
Yeah.
You mentioned DSI before. The corrected supernova data now aligns with models favored by projects like DSI, which used baryonic acoustic oscillations, BAO, and the cosmic microwave background, CMB.
Right. Two pillars of modern cosmology completely independent of supernovae.
We hear BAO and CMB mentioned a lot, Maybe let's quickly recap what they actually are, why they're reliable cosmic rulers in their own right.
Good idea. So the CMB, the cosmic microwave background, that's literally the oldest light in the universe we can see.
The afterglow of the Big Bang.
Pretty much. It's the residual heat and light left over from about 380,000 years after the Big Bang. That was when the universe cooled down enough for electrons and protons to finally combine and form neutral atoms.
It's called recombination.
Right. And that event essentially made the universe transparent to light for the first time. So the CME gives us this incredible snapshot of the universe when it was extremely young and incredibly smooth, but with tiny temperature fluctuations. These fluctuations were the seeds of all future structure.
Okay, that's the CMB, a picture of the early universe. What about BAO? Baryonic acoustic oscillations? Sounds complicated.
It sounds complicated, but the concept is actually based on sound waves. Think of the very early universe, before recombination, as this incredibly hot, dense soup, a plasma of particles and light.
Got it.
In this soup, you had gravity trying to pull matter together into clumps, but you also had intense radiation pressure from the light pushing outwards. These two competing forces created ripples, actual sound waves or pressure waves, sloshing through the plasma.
Like sound waves in air, but in the primordial soup.
Exactly. Now, when recombination happened and the universe became transparent, the light decoupled from the matter, and those sound waves basically froze in place. They left behind a subtle imprint. Slightly denser shells of matter at a very specific, predictable distance from the original clumps.
Ah, a characteristic distance scale imprinted on the matter distribution.
Precisely. The size of these frozen spheres corresponds to how far a sound wave could travel in the plasma before recombination happened. We can calculate that distance, called the sound horizon, from fundamental physics. It's a known quantity.
So it acts like a standard ruler.
A standard ruler, exactly. So today, when astronomers map the distribution of millions of galaxies across the sky, they look for a slight statistical preference for galaxies to be separated by that characteristic BAO distance.
They look for that bump in the correlation function at that specific separation.
That's the one.
Yep.
And because we know the actual physical size of that ruler, sound horizon, by observing its apparent size on the sky at different distances, we can measure the expansion history of the universe completely independently of supernovae.
Okay, so BAO and CMB are powerful, independent tools. How does the corrected supernova data line up with them now?
That's the key convergence. The conclusion from the corrected supernova data that the universe is decelerating today agrees remarkably well with what was independently predicted by analyses using only BAO data, or BAO combined with CMB data.
So those other methods were already hinting at deceleration.
They were hinting at models that preferred deceleration today, or at least were inconsistent with strong ongoing acceleration. But as Professor Lee pointed out, this alignment had previously received little attention, primarily because the uncorrected supernova data, which everyone trusted as the gold standard, pointed so strongly in the other direction, towards continued acceleration. The discrepancy was usually blamed on potential issues with the BAO-CMB analysis, not the supernovae.
But now the tables have turned.
Exactly. Now that the supernova data itself has been refined and corrected for this well-motivated stellar age bias, all three major lines of evidence corrected supernovae, BAO, and CMB seem to converge. They all point towards the same picture, a universe slowing down today, driven by a dark energy that is weakening over time.
That kind of convergence from independent methods is incredibly powerful in science, isn't it?
It's the strongest validation you can hope for. It suggests the age bias correction isn't just some statistical fluke, but reflects a real physical effect that brings different cosmic probes into agreement.
And this convergence also helps with another big headache in cosmology, the Hubble tension.
Yes, it potentially offers a significant step towards resolving the Hubble tension.
Remind us what that is again?
The Hubble tension is this persistent and statistically significant disagreement about a 10% difference between measurements of the universe's current expansion rate, the Hubble constant age error.
A disagreement between which measurements?
Between measurements derived from the early universe, primarily the CMB data analyzed within the standard CDM model, and measurements made in the local or late-time universe, which heavily rely on things like type Ia supernovae to build the cosmic distance ladder.
So, early universe measurements give one value for age, late universe measurements give a higher value.
Correct. And the discrepancy is statistically significant, meaning it's unlikely to be just random error. Now think about it. If the foundation of that late-time measurement, the type Ia supernova distance scale, was systematically flawed.
Because we thought they were brighter than they actually were, especially the distant ones due to the age bias.
Exactly. If they were intrinsically fainter, then our distance calculations based on their apparent dimness were systematically underestimating their true distances.
Making them seem closer, which inflates the calculated expansion rate.
Precisely. If the distances were wrong, the local H-zeros derived using them would appear artificially high. By recalibrating the supernova distances using this age bias correction, their inferred distances should increase, bringing the late-time H-zero measurement down, potentially closing the gap with the early universe value derived from the CMB.
So fixing the standard candle doesn't just change the future fate of the universe, it helps reconcile its past and present expansion rates.
It has the potential to do both, yes. It addresses a fundamental calibration issue that ripples through cosmology.
Now, to be absolutely sure about this, the Yonsei team isn't just resting on this correction, right? They're planning more tests.
That's right. They're already working on what they call an evolution-free test.
Evolution-free, how does that work?
It's actually a really clever way to directly test their hypothesis. Instead of trying to mathematically correct for the age bias, they're trying to eliminate it from the sample selection itself.
Oh.
They are selecting supernovae by only comparing explosions that happen in host galaxies of the same relative age, coeval galaxies, but across the full range of cosmic distances, redshifts.
So comparing apples to apples. Young stellar populations only with other young stellar populations old with old.
Exactly. By comparing with across cosmic time, they aim to remove the age metallicity evolution as a confounding variable in the distance measurement entirely. If their hypothesis is right, this evolution-free sample should still show the deceleration trend, even without applying the correction factor.
And are they getting results from that yet?
The paper mentions that early results from this evolution-free test already seem to support their main conclusion, reinforcing the deceleration picture. But to really put the nail in the coffin, methodologically speaking, they need much, much more data.
An explosion of new data, you might say.
Yeah, quite literally in this case. And that's where the next generation of astronomical observatories comes in, specifically the Virasi-Rubin Observatory.
The new big telescope in Chile.
Exactly. It's located in the Chilean Andes, just recently began its scientific operations, and it houses the world's most powerful digital camera. Its main job, the Legacy Survey of Space and Time, LSST, is to repeatedly map the entire southern sky over 10 years.
And it's going to find a lot of supernovae.
An unprecedented number. Crucially for this topic, the Rubin Observatory is expected to discover and characterize type Ia supernovae with incredible speed and precision. We're talking potentially tens of thousands of them.
Tens of thousands, compared to the hundreds used in current studies.
Yes. The estimates are that within the next 5 years or so, Rubin could discover and provide detailed host galaxy information for more than 20,000 new supernova host galaxies.
Wow.
This enormous data set, combined with Rubin's ability to get really precise measurements of the host galaxy properties, their ages, their metallicities, will allow for what the Yonsei researchers themselves call a far more robust and definitive test of supernova cosmology.
So this is really the moment of truth coming up in the next few years.
It really is. We will finally have the statistical power and the detailed data needed to either absolutely confirm this age bias correction and the resulting deceleration, or perhaps find nuances or flaws in the theory. The data will decide.
But let's assume for a moment it is confirmed. What are the biggest, broadest implications for how we understand the universe?
Well, if confirmed, it's arguably the most significant paradigm shift in cosmology since dark energy itself was discovered nearly 3 decades ago.
That's a huge statement.
It is. Firstly, as we discussed, it potentially resolves the nagging Hubble tension by fixing the fundamental distance scale calibration. That's big.
Okay.
Secondly, and perhaps more profoundly for the ultimate fate of the universe, it gives us crucial clues about the physical nature of dark energy itself.
How so?
Because if the universe is decelerating today, dark energy simply cannot be the simple, unchanging cosmological constant described by ACDM, where W is forever fixed at Mection 1. It must be something dynamic, something transient, something that weakens over cosmic time.
So it's not a constant property of space, but more like a field or force that's fading away.
That's the implication. It shifts our focus dramatically. Instead of thinking about a static, constant energy density filling space, we have to consider a dynamic, evolving component of the cosmos, one whose influence peaked in the past and is now waning, allowing gravity to gradually regain dominance on cosmic scales.
Okay, let's try and pull this all together then. Recap the core argument that's challenging, 30 years of cosmological thinking.
Right.
We started with the assumption, the bedrock really, that type Ia supernovae were perfect standard candles, uniform brightness everywhere, every time.
The 100-watt bulbs of the cosmos.
Exactly. And that assumption led us, via observations of their unexpected dimness at great distances, to conclude the universe was accelerating, driven by a constant dark energy, CDM.
That was the picture.
Now, new research, backed by this incredibly high 99.999% confidence level, shows those candles are actually flawed. There's a systematic bias linked to the age and metallicity of the stars that explode.
Younger metal-poor systems produce intrinsically fainter supernovae.
Right. And when you correct for that bias, the picture flips. The corrected data suggests the universe is no longer accelerating, but has actually transitioned to a state of deceleration right now, today.
And proving or strongly suggesting that dark energy isn't constant. It weakens. It evolves over time.
So this isn't just some academic debate about cosmic speed limits, is it? It fundamentally changes the story of our universe's ultimate destiny.
Absolutely. It's about the end game for all matter and energy. If dark energy's nature is changing, if it's weakening, then the end might not be the endless, cold, accelerating expansion, the so-called Big Rip, or eternal heat death that the Standard Model predicted.
So the universe doesn't necessarily rip itself apart or fade into cold darkness.
That scenario becomes much less certain. Knowing how dark energy evolves, how quickly it's weakening, becomes absolutely essential for predicting the future, especially if gravity is indeed starting to win the cosmic tug-of-war again.
If dark energy is weakening and the universe is already slowing down, where does that road lead? Does expansion just stop?
It could. The focus shifts completely away from runaway expansion. If the density of this evolving dark energy continues to drop, theoretically it could eventually fall below the average density of regular matter and dark matter.
And then gravity really takes over.
Then gravity would be the undisputed dominant force on cosmic scales. Deceleration would continue, potentially until the expansion halts entirely, and then reverses.
Reverses, meaning contraction.
Meaning the universe could start collapsing back in on itself, heading towards an eventual recollapse.
So we go from worrying about big rip to potentially facing a big crunch, like the old cyclical universe ideas.
That's the dramatic alternative that re-enters the realm of possibility if this evolving dark energy model is correct. You mentioned the source material hinted at related research suggesting the universe might end in a big crunch around 33 billion years from now.
Yeah.
Well, that kind of scenario suddenly moves from speculative fiction back into the arena of scientifically plausible futures, depending on exactly how dark energy behaves.
Which leads to a final thought for people to chew on.
If deceleration continues, if contraction eventually begins, what does that mean for our fundamental understanding of gravity and vacuum energy and space itself? What allows the universe to put on the brakes and actually reverse course?
That's a deep one. What fundamental assumptions have to change?
Exactly. It's a profound question to mull over.
And thankfully, it's a question we might get a much clearer answer to soon. Thanks to that flood of incredibly precise data we're expecting from the Vera C. Rubin Observatory over the next few years.
That's where the next chapter of this story will be written. Waiting to see if the light from thousands of new supernovae confirms this cosmic shift, potentially from eternal expansion towards an ultimate collapse.
An absolutely fascinating turn in our understanding of the cosmos. Thank you for walking us through that.
My pleasure. It's a truly exciting time in cosmology.
And thank you for joining us on this deep dive into the very fabric of space and time.